All right, so I'm waiting for the recording to start, so that's why I'm kind of pausing for a while. And we will start the lecture today with this concept called referential integrity, uh, or referential integrity constraint, or just simply referential integrity. And all these integrities that we are going to be talking about, if you do a little bit Google search, you just search for database integrity, right, or data integrity in general. A typical web page or the answer you find on Google search might give you 3, 4 different integrity. And one is something what we call the domain integrity. The second we'll probably call the entity integrity. And we have the third type, it's called the referential integrity. And the fourth type usually we'll see is called a key integrity. So the domain integrity, entity integrity, referential integrity, and key integrity are 4 different integrity we use to describe how you control the data quality in your database, right? So we'll see example in the lecture today. So basically, the foreign key we saw in the previous lecture is a mechanism used to control the referential integrity. And let's put in this way, using the example to describe why the referential integrity is important, right? So if you have a referential integrity or foreign key relationship, like what you see in this example, the student ID or the student ID is put into this entity or table called class, right? So what this means is that and we have some concept of if you look at this class, you have employee ID and SID. So you have a student ID put into the employee ID class of some sort. And the second table will have a foreign key. So the first table does not have foreign key on the left, but the second table has a foreign key. When the second table has a foreign key, then your student ID cannot be missing or does not have value. Say for example, right? Just put this into more perspective. We'll probably see more example in real data later. Imagine on this table, and now this is actually part of training as well. You have to look at this schema description and try to imagine what kind of data you can see in these tables. Imagine we have the table says student SID is 001, 002, 003. So 1, 2, 3, 4, 5. Let's assume that for all the graduate we have from UIS we have 25,000. So your student ID from 1 to 25,000. So the maximum number is 25,000, right? So if you see 25, so if you go to another table and this table is called class. I don't know what this table represents or meaning, but it could be a registration record. So if you see a registration record of some sort that lists the class number, or in this case, the employee ID may be the professor's number and the student number, and you see a number there says 30,000 on the SID column. So what does that mean? It means that we have a student or either coming from the future or it has never existed registered to your class, right? So if you have that kind of data record, it shows that there must be something wrong with the database, because this number 30,000 has not been issued by our database system, but you see in your data record, right? So that's the data conflict. It's some sort of inconsistency that you can observe from the database, and this is obviously a database problem. And why this is happening, we don't know, but we know it's a potential problem, right? And this is especially true if you put this into a perspective of a business. This type of missing data or imaginary data or strange data coming to your database, a lot of time in accounting, we consider this a potential red flag for a fraud, right? So Now, if you want to kind of laundry money for using using some sort of an entity. By the way, I was watching this Netflix series called Ozark. They were talking about laundry money. Very very interesting. So you're but we are talking about laundry money in here, and then you want to create this fake record. So if you insert a data set that is not in your say client database, and nobody can track unless you really try to dig it out, right? So from a database designer's perspective, we have to prepare to make sure that this kind of fraud cannot be committed, right? But of course, for the and those of you who are more interested in security or some other issue, that you know that there are a lot of mechanisms to do that. And one of the modern or more recent technologies called the blockchain technology can be used to make sure the data integrity is protected by a digital contract between the blockchain. But in this case, relational database itself building this constraint called referential integrity constraint. If you design the database correctly and enforce the constraint, your database is to a certain degree be protected. This actually ties to the purpose of what we are trying to do here, the normalization theory. And normalization theory is used to try to make sure the integrity constraint is protected, right? So a long description about the why we need these constraints and how these constraints will be enforced using normalization theory. Using the database schema method of describing the constraint, it's usually written in a way that with a where statement, right? And later in again our chapters, when we start talking about the data or so-called the data definition language, and you actually see some of those already in our example, even though we have not officially introduced these SQL keywords. Now, when you create a table or create a view of some sort, the create view is something we consider as data definition language. In data definition language, we'll use a schema language similar to this. So we will write a constraint says, okay, there is a constraint says order item, this particular key have to exist in a particular table to make sure that it's there, right? So once you specify this constraint, the database management system engine, right? So this SQL Server, Oracle, this software will automatically enforce. So when somebody enters incorrect information or data in there, the system will stop the user or program from insert or delete or update the data set, right? So that's the importance of integrity or referential integrity in this example. Now, so talking about the integrity and the database or data problem, and it's actually a data integrity problem usually coming from 3-4 different places. And I put a little acronym just to simplify our understanding or memory of all these terminology. It's called, and this kind of problem we have a jargon, we call this anomaly, or database anomaly. Anomaly is something not normal, right? So, and specifically it's called a modification anomaly. It includes 4 actually things, but the fourth one is not listed on my acronym here. The fourth one is called create. So when you create something, you can create something incorrectly. But other than create something correctly, in particular in database, we'll be creating table incorrectly. You can delete something and then generate some inconsistent data, or you can insert something and generate something consistent. You can update something, then you can update something consistent. Going back to the previous example, I kind of verbally describing when a student registers to a class, a student record is like 10,000. All right, 10,000 is a legitimate number. We said already that So far we have from 1 to 25,000. So 10,000 is a legitimate number. But for some reason that because maybe this student committed a crime or that doing something that not legal, and you decided we're going to be deleting the student or actually retrieving our degree from the student, even though the student graduated. So you go into your database, delete the student record. So now your database has the student, does not have the student record 10,000 anymore. However, your class registration record may still have some record with student 10,000. Now, what's wrong with that problem then? The problem will be when you try to search for the information of student 10,000, you cannot find it, right? So, so that is possible. You can go back and you try to do some investigation or data mining of your old database. You cannot find that student anymore. So that's problematic. That's create database problem already. Similar situation can happen in other occasion when you are updating, change the value of the database, when you are inserting a new record of the database, all these can create similar database problem. So we call them modification anomaly. There are 4 of them, and 3 of them is remember as DUI, driving under influence, or delete, insert, and update, or delete, update, and insert. And the 4th one is create, right? So DUI level C crime. That's usually how I remember it. Right, the UIC, driving under influence, level C, very level A, 0.05, level C, level B, 0.10, alcohol level content, level C, 0.20. You have to go to jail immediately if you're level C offender. Right? Anyway, right. So let's take a look at some of the data problem that we might encounter in the database, and this is usually happen when somebody try to put a manually inputted data set such as an Excel spreadsheet into a database. Right? So let's take a look at this, and the practice like this is something also we consider as so-called the data consciousness. Right? So you have the data awareness or some sort of, when you look at a dry data set, you become very analytical and try to find out what's wrong with it. Right? That's actually a good habit or good practice for any person handle data. And you know, yeah, I should not go into that too much about the personal story, but let's take a look at this table. The problem of these two tables, or the table here, are the consistency in between the data column, right? And it's assumed consistency. Now I'm explaining to you why. And if you look at the table on the top, we have item number and equipment type and acquisition cost. So look at the first 3 columns for now. And if we see item number 100, we see the equipment type is the drill press. We see the item number 200, we see equipment called lathe, right? So it's a rotating cutting machine. And drill and lathe and mill, of course, that if you are a guy like to do garage work, and then you know all these machines or tools that you are using. And so 100 is drill press, 200 is lathe, 300 is mill, right? And if you and so if you check the data, all the 100s are drill press, no problem. 200 lathe, 300 mill, no problem. And so there's no problem, no problem in terms of consistency between item number and equipment type. If you see something says item number 100, but the equipment type is mill, there's something wrong with it, right? So in this case, the first 2 columns is consistent, no problem. But if you see the 3rd column says acquisition cost, the drill press 100, the first record, first row here, actually I should avoid using record. First row here, 3,500, right? And so if you see the row number 3, item number 100, drill press, same equipment, acquisition cost 3,500. So if you check all the 100 item number, their costs are all the same. It seems to be making sense, right? Yeah, so I buy the same equipment. If they are the same item number, same model, should be the same cost, right? And they are purchased about the same time, 2011 something, if you look at the data later. But if you look at the table at the bottom of the slide, you notice one thing. In the row number 6 on your lower table here, the acquisition cost for drill press become 5,500, right? So there is a problem now that if in that actually your textbook assume the table on the top is the uh, original data set from a spreadsheet. Table at the bottom is the uh, table that probably generate or so-called entered into your database manually, right? So maybe somebody has a typo when they try to type acquisition cost in here. Then that creates this data inconsistency. So you have two copies of the database, but the one there's some inconsistency in the data set. So that's where the problem is. And this is usually generated during the insertion process, right? So this kind of problem, can we somehow design a system to avoid it, right? That is actually where normalization come out. So this is a anomaly that we usually observe in database, especially when you try to move data from one place to another, or try to duplicate the data for backup purpose or something, that you see this. Right. But of course, this issue leads to a lot of discussion in business operation. So the 5,500 unit cost or acquisition cost for drill press, is that correct or not? Or the 3,500 should be correct? Which one is correct? That's another business discussion, because maybe, during a crisis, pandemic, suddenly the drill press equipment increased the sale price. It's possible, right? So how and why it's not, how and why and this data inconsistent happen is not our discussion here. But technically, as a data manager, you have to be aware this is a problem, right? So to resolve using from database design's perspective to prevent you from enter manually the incorrect data, and the normalization theory was created. There are 1, 2, 3, 4, 5, 6, 7 different normal forms. Let's start with the first normal form, second normal form, third, BCNF, fourth, fifth, and DKNF, right? So there are 7 different normal forms. In practice, people usually go into only fourth normal form, meaning that 1, 2, 3, BCNF, and 4. And a lot of time, general practice, BCNF is also ignored. So we're doing 1, 2, 3, and 4. So that's 1, 2, 3, 4 normal form is usually sufficient from the learning's perspective. And your textbook, because we are engaging in more like a graduate level discussion, include BCNF. But believe me, it can be very confusing if you dig very deep into this particular topic. But just remember from my lectures purpose, I want you to remember that in practice, for most of the operational database, operation means that the database you are using is actually used to handle day-to-day operation, like for handling sales, handling say uh, uh, registration for university, handling that handling what handling anything that happen very frequently. Operational database, inventory control, for example, will be another example. Customer relationship management, all these operational type of database, we normalize the database to the fourth normal form, right? And there's another type of database called readable or data warehouse type of database. We'll move forward. Now, a note from your professor here from the education purpose. In the modern database world, especially from the business school, normalization theory will be not emphasized that much. In the past, when I was learning database, was in the 80s, 1980s. This is extremely important. We spent about when I first took the database, the relational database. Actually, we were still using hierarchical database back then. but the relational database was introduced when I was in college. And we spent about almost 2 months in the entire semester talking about normalization theory. But in here, we intend to spend only 2 weeks in our discussion here. So that tells you that how little we touch on this topic. It can be very, very difficult if you really get into the mathematical part of the theory. But for our purpose, we want to understand conceptually and know exactly what they are doing. And again, like we say, we are going to be going to force normal form only. We're not going to go beyond force normal form. Right? And first normal form is a table qualified as a relation is a first normal form. So no waste of space, no duplicate record. That's what we talked about from previous lecture. Second normal form is a relation or table. Use relation and table interchangeably. In the second normal form, if the attribute used as a primary key can determine all the non-primary key attribute or column. Right, so that's second normal form. So primary key is validated is your second normal form. So a good primary key, correct primary key is the second normal form. And we'll have a lot other lecture talk specifically on primary key, how good is a primary key. Third normal form is a normal form if your table is in the second normal form, and then there is only one primary key and there is no other candidate key. It's called the third normal form. And the BCNY or Boyce-Codd normal form is a relationship that every determinant, every primary key is a candidate key. So there is no non-candidate key determinant. And this Boyce-Codd normal form, in a way, it probably take a little bit more time to explain, but basically that we were going to be using an example to understand the concept, but that should be enough. And BCNF related to just simply using comments here, relates to multi-column or multi-attribute key. Multi-column key usually create a problem or BCNF. Usually when we select a key, primary key, we try as much as we can select single column. But sometimes single column cannot serve the purpose of determining every other column in your table. So we select multiple column. And last lecture we used the example of if you want to create a small database like in our class, we can use first name as a primary key. But first name is dangerous because there are a lot of duplication. So if more than person is called Michael, actually when in the 80s, Michael was the number one boy's name in the United States. And I think in 2000, the number one is either Alex or something along that line. But anyway, so that's so there are a lot of people called Michael. So if you use the combination of the first name and last name, that reduces the possibility of your data will be duplicated. So that's so you use first name and last name. And but still, a lot of people is the same first name and last name. If you put more information here, you put a third column, middle name. It reduces the possibility of duplication even further. But still, you cannot avoid the duplication. If you introduce a social security number, then that reduces the possibility almost to zero, right? Even though that it could possibly that you have duplicate social security number, right? I leave that my statement earlier about duplicate social security number as a point of your imagination or further research. So try to see research on the social security number to see how it was established, how it is used and recycled, then you'll know that it's possible. Social security number can be duplicated in a database, right? Or you can see duplicate social security number in the database, right? Simply saying, by the way, how many digits in the social security number? 10 digit. 10 digit is the combination of 10 digit can generate slightly one less than 1 billion combination. And if you think about how many people we have in the United States, about 300 million, 330 million in population, right? So the combination of Social Security number can generate about 3 times as many combination or number for the U.S. citizen. But if you try to think of them a little bit further, you'll find that, well, we have 330 million people now, but after 100 years, see, all the 330 million people die, assuming the population of the United States does not increase that much, and there will be one generation all die out, and the other generation come in. The other generation has another 300, 400 million people. If you rotate the generation for 3 generations, then you have more than 1 billion people you need to kind of mark and number. You run out of Social Security number. So how do you deal with the situation that you run out of Social Security number? And that something that go beyond our lecture here, but I'll pose that research question for you to think about. All right. So the process of normalization is actually very simple or very confusing. It's all documented on this table from your textbook already. And you go 1, 2, 3 steps, and you have the normal form up to the third normal form. Right? And we can probably take a look at one. And this is a slide that kind of using another method called the alternative, go straight to BCNF method. Your textbook calls this go straight to BCNF method of normalization. So this is another process that you can go through, and I'll encourage you to read this and think about it a little bit more by yourself to understand this better. Of course, when you have more time and very quiet time, you can focus and concentrate and think about how to do this. But in practice, let's take a look at how this is done in a typical database design or redesign problem. So we have this typical table, most likely from Excel spreadsheet, and we have the schema written already here as an equipment repair. Here's a table, has item number and repair numbers and a lot of columns here. You know, if you study database for a while, you understand immediately that this is a join table with a combined two concepts, and one is called equipment, the other is repair. Equipment is a somewhat like a physical object, right? Repair is a concept of an event or a job to be done, like sales. Sales is an event. It's something happened that you want to record that particular event happening. So repair is a service job. In business, it will be a service transaction. And by the way, that I just mentioned a extremely important keywords in my previous sentence called transaction. Right? And later we'll come back to discuss transaction a little more. But for now, keep that in mind. Transaction management is a very important concept in database management. If you can handle transaction, your database is usually running more or less smoothly for the operational purpose, inventory control, student registration, even the exam management or quiz management. All these are transaction. Right? So transaction is a big concept, and entity or object is another concept. In this case, equipment are like entities, physical entities, and repair is a transaction, more conceptual concept. So the schema is written this way. Our job is to redesign this table into normal form, right? So that's the test is all about in normalization theory. So the process goes something like this, and first the normal form is that when every table you can describe this as relation, it's already a first normal form. So the equipment repair is already a relation, and because we didn't see and if you look at the data, that every row is occupied, there's no empty cell, no waste of space, and there is no duplicated record, and so it's every record is by itself, and we have a first normal form. So do nothing, you already have first normal form, because by definition, a relation is a first normal form table. And second is that we're going to be identify all the possible primary key as identify all the candidate key as a primary key. And the second, we have a primary key called repair number in the original, right? And just try to think conceptually. If you know repair number, in real time does repair number ties directly to the cost of the equipment you're trying to repair? Logically could be, but it's not 100% proof. So the primary key, when we talk about determinant last week or last lecture, that we need to know that if I know repair number, can I 100% for sure I know item number, equipment type, acquisition cost, repair date, and repair amount? Right? If that answer is I'm not quite sure, then you have to select another primary key. Or alternative is you have to split the table into multiple tables, so each table has its own primary key. So in this case, we split this table into multiple tables. Each one of them has a primary key, item number. So now if we look at the equipment, you know the item number, you know everything about that equipment. Good. Repair is a concept. You know the repair number, you know the information about repair from that repair number. So this makes more sense in the after normalization. So this is a second normal form. Right? So we are in the second normal form. The BCNF normal form is actually already in place here. The reason being that this one does not have multi-column attribute as your primary key. So we have achieved BCNF already. So very quickly, we look at the table and we identify primary key. We are almost in third normal form already. And we check the third normal form, and actually it's already in third normal form. Every column is it, and there's no other potential candidate key for the column, so they are in the third normal form already. And the only job we have remaining to do is to do the fourth normal form, which will be explained in the next few slides. And so very quickly, using this example, you know that normalization is not that hard as long as you can identify primary key and know the definition of table and make sure that you do not have other candidate key. You will reach almost all the normal form that required for operational database. And we will stop this lecture here to keep the time of each lecture within about 30 to 35 minutes, and we'll continue the lecture in the next part of our normalization lecture.